So today's topic is internal energy and change in internal energy. Internal energy is sum total of all types of energies present in a substance. Means, every substance possesses a definite amount of energy, a certain definite amount of energy, and that energy is called internal energy. Okay, and that internal energy is denoted by U, or in some cases it is denoted by E, capital E. Good evening, Sameer. Right? So, every substance possesses a certain definite amount of energy, and that is known as internal energy. So, actually internal energy of the substance depends on which factor internal energy depends. So, internal energy depends on, yes, its nature, okay, and it also depends on conditions of temperature and pressure, okay. Right. So, actually internal energy, like if we have 1 mole of water, so 1 mole of water has different energy at different temperatures. That means it depends on mainly temperature, okay. Let us consider we have 1 mole of water, okay. Now 1 mole of water, at 280 Kelvin and at 290 Kelvin or at 300 Kelvin. So at different temperatures it has different amount of energy. Internal energy is different. At different temperature, okay. So now every substance is made up of atoms or molecules. That all that every substance is made up of atoms and molecules, okay. So whatever energy is possessed by atoms and molecules, that is the energy of the substance, okay. So what it means, substance has atoms and molecules, so its internal energy is what? Is the sum of energies, okay, of the atoms and molecules. And they like we have electronic energy or nuclear energy. Energies are of different types: bond energy or translational energy, rotational energy, vibrational energy, means in a nutshell means all types of energy is known or unknown to you. The sum of all types of energies is equal to internal energy of the substance. That means what is internal energy actually? It is sum of all types of energies possessed by a substance, and those energies are electronic energies, chemical energy, nuclear energy, electronic energy, translational energy, rotational energy, whatever type of energies you can name, all types of energies, sum total of all types of energies present in the substance or possessed by atoms and molecules present in the substance, that is called internal energy. Now, it is not possible to measure exactly the different forms of constituting energies. Therefore, it is not possible to know exactly the internal energy of the substance. So, keep in mind, we are not able to know exactly the internal energy of the substance. Okay, means absolute value of internal energy of a substance is not possible to calculate. Absolute value of internal energy of a substance is not possible to calculate, or we cannot measure the absolute value of internal energy. We cannot measure the absolute value of internal energy. Okay, so that means what we can calculate change in internal energy. Keep in mind, we can calculate change in internal energy. Now, change in internal energy. Now, to calculate change in internal energy, what is internal energy change? It is the difference in the internal energies of the products to the internal energy of the reactants involved in the reaction. Okay, suppose we have a reaction, in a reaction reactants are converted into products. So, what is change in internal energy? That is equal to internal energy of sum of the internal energy of the products minus sum of the internal energies of the reactants, or we can write simply UP minus UR. Okay. So, the value of delta U may be positive or negative depending upon the relative energies of internal energy of product or reactant. Like the value of delta U is positive. Yes, when it is positive. Yes, when it is positive, if internal energy of products, sum of the internal energies of products is greater than sum of the internal energies of the reactants, and is negative. Yes, when it is negative, if internal energy of the product is less than internal energy of the reactants. Okay. So, what it means? It is not possible to determine the exact values of the internal energies of the products and reactants taking part in the reaction, but the problem can be solved by carrying out the reaction at a constant temperature and volume. So in that condition, what we do? If temperature is constant and pressure is also constant, temperature and volume are constants. Tell me, what is the work done? Work done is 0. So when temperature and volume are constant under the conditions delta V is 0, very good, very good. No work is done, very good. Okay, good. So no work is done. Okay, on the system or by the system. Okay, no work is done either by the system or on the system, because delta V is 0, so W is 0. Okay, so internal energy means, what is the change in internal energy? Either work is done or heat is exchanged. So now what is left? So that means when volume is constant, so the amount of heat energy exchanged, between system and surrounding under these conditions or simply write amount of heat energy exchanged between system and surroundings at constant volume is known as change in internal energy. So it means that delta U is equal to QV. So this V indicates that heat exchanged at constant volume. So change in internal energy is simply the amount of heat exchanged between system and surrounding at constant volume. Okay, so heat energy exchange between the system and surroundings at constant volume as well as temperature, because if volume is constant, temperature is constant. Okay, heat energy exchange at constant volume and temperature. So that is called internal energy change. Okay, Namita, good evening. So now derive, if question is derive expression for derive and define first law of thermodynamics. Okay, or question may be derive the relation delta U equal to Q plus W, or it may be define and derive law of conservation of energy. If question is any of them, there is a same answer, because this is the mathematical form of first law of thermodynamics. Delta, you know it is change in internal energy. Q is heat absorbed or evolved by the system, and W is work done on the system or by the system, right? So what is law of conservation of energy? That is actually the first law of thermodynamics, that when energy is exchanged, okay, between system and surrounding, or any two systems, okay, in any form, one form to other, okay, and any energy change is constant. Total energy of the system and surroundings is always constant. Sum total of energy of the system and surrounding is always constant. Energy may change from one form to another, but total energy change is always same, and that is called law of conservation of energy, and it was given by Helmholtz. Okay, so statement is energy cannot be created or destroyed, although one form of energy can be converted into other form and vice versa. So first statement of first law of thermodynamics is energy can neither be created nor energy can neither created nor destroyed. Okay, although one form can be converted into the other form. And vice versa. Am I right? Okay, Animesh, energy can neither or nor destroyed, created, but can be changed from one form to another. Very good, very good. Right. Okay, or it can also be defined as sum total of the energy of the universe remains constant or is conserved during any physical or chemical reaction. Means the sum total of the energy of the universe. Universe means everything is included in it, right? Universe means system plus surrounding, right? The sum total of the energy of the universe remains constant. Or is conserved during any physical or chemical reaction. So that is the second definition. Meaning is same, you can write any one, okay, because first is energy can neither be created nor destroyed, although one form can be converted into other form and vice versa. And second is sum total of energy of the universe is always constant, okay, during any physical or chemical change. Any other? So that now next definition is that if a certain amount of energy in one form disappears, then an energy reappears in equivalent amount. Means whenever a certain amount of energy in one form disappears, then an equivalent amount of energy in another form reappears, means it cannot be destroyed. Means there are some vibrations. Every activity has some vibrations that cannot be dissipated, that can be converted into another form. Okay. Or last definition is, it is impossible to construct any machine, okay, which could perform work without consuming any energy. Means if you do some work, there should be consumption of energy. Means it does work at the cost of energy. There is no machine as such, it cannot be constructed that will not consume any energy and produce work. Okay. So fourth definition is, it is impossible to construct a perpetual motion machine. Okay. Perpetual motion machine means that is a machine which could perform work without consuming any energy. So these are the definitions. Okay. Yes, these are the definitions of first law. Beta, for example, say we are moving turbine. Okay. When turbine moves with the help of water, then that produce electricity. So that means one form of energy is converted into another form. It cannot be dissipated. According to first law, that whenever energy is consumed, an equivalent amount of energy is reappearing. So this is the best example, that water is used to move turbine, and on moving that turbine, electricity is produced. So electricity is the work done or energy produced with the help of that motion of water, okay, with the help of turbine. So motion of water which moves the turbine is converted into useful work. Got it? Animesh, dW equal to PdB means small amount of work done when there is a small volume change. Okay. Okay, so these are the definitions of first law of thermodynamics. Now mathematical representation. Okay, mathematical representation of first law of thermodynamics. So what we do, let us suppose, because we have to suppose, reason being we don't know the exact internal energy. Okay, so let us suppose system has internal energy equal to U1. Initially it has internal energy U1, and U1 we cannot calculate. Okay. Now, if this system absorb heat, if it absorbs heat Q from the surroundings, now this system absorbs heat Q, okay, from the surrounding, okay, and at the same time, if work W is done on the system, right? If W is work done on the system, then the final internal energy that is equal to U2. Tell me, what is U2? Yes. Then final energy equal to U2 will become, yes, can you write it like this? So tell me, U2 is equal to, initially internal energy is U1. Now Q is the heat absorbed by the system. So Q is heat absorbed, okay, and W is the work done on the system. Both have positive sign. So final internal energy is equal to initial internal energy, that is U1 plus Q plus W. So U2 minus U1 is equal to Q plus W. That implies delta U is equal to Q plus W. So change in internal energy equal to, yes, this change in internal energy delta U, change in internal energy is equal to heat energy added to the system right plus work done on the system, right? Now tell me, in case W is work done by the system, then delta U is equal to Q minus W. Delta U equal to Q minus W, or Q is equal to delta U plus W. Is it right? So these are the mathematical forms of first law of thermodynamics. What we do, if we consider U1 as the initial internal energy of the system, Q is the heat absorbed by the system, W is the work done on the system, then U2, that is final internal energy, is equal to initial internal energy plus Q plus W. Because heat absorbed has positive sign, we have already done that sign conventions. System, if system absorbs energy from the surrounding, Q is positive. If system releases energy to the surrounding, Q is negative. If work is done on the system, W is positive. If work is done by the system, W is negative, right? That we have done already, okay. So, U2 minus U1 becomes equal to Q plus W. So, you know, change in internal energy, that is equal to Q plus W, and you know, Q, we know that how much heat is added to the system and how much work is done on the system, that we also know. So, we can calculate delta U, but we cannot calculate U1 and U2. We are not able to calculate U2 and U1, but we can calculate delta U, or sometimes we write it as delta E, okay. So, let us do next part. Now, let us prove that internal energy as a state function. Yes, your test now. What is state function? The variable or the property, the variables or the properties whose value depends on initial and final state of the system and is independent of the path followed. Abhijit, function defined for system relating several state variables or state quantities that depends only on the current equilibrium thermodynamic state of the system. Okay, value does not depend on the path taken to reach the specific value. Yes, so it depends upon the yes, means Ralam, you are right that their temperature, pressure, or a number of moles. Okay, they are all state functions. But question was, what is state function? I am not asking you the examples of state functions. Okay. We have to prove internal energy as a state function. So, we should know what is state function. So, state function means any property or variable whose value depends on the initial and final state of the system. Means that depends upon the, yes, Abhijit is right, that depends upon the current state of the system. Okay. Okay, right. So, let us prove. Suppose we have pressure and volume graph. Okay. Now, system is at position A. Okay. Now, at A, its internal energy is U1. Okay. Let us take U1 as its initial internal energy, and now by following path 1, it moves to state B. Now, its internal energy is U2. Okay. This is path 1. Okay. A to B. Now, this B moves back to A by following another path. Path 2. So, tell me, when, see, paths are different. Oh, it's okay, it's okay. Path 1 and path 2. Now, tell me, after reaching at position A, is there any change in the internal energy of the system? See, first A moves to B by adopting path 1. Okay. Then B moves back to A by following path 2. My question is there any change in internal energy of A? after reaching A, its internal energy remains U1 or it is different. Let us take its internal change in internal energy as delta U1, and here change in internal energy as delta U2. Is there any difference in the magnitude of delta U2 and delta U1? Very good, Abhay. There is no difference in their energies. Okay. If it is a path function, sorry, it is a state function. Paths are different. So, maybe Q and W are different. Q and W are different. That means Q and W are path functions. Q and W are path functions. But Q plus W, that is delta U, is same. Q plus W is same. Chitra, Abhijit, they are not different, they are same. That's why, because it depends upon the state. See, in this case, it is U1 and U2 minus U1, delta U1, that is U2 minus U1, and delta U2, that is U1 minus U2. So, their magnitude are equal. Okay, magnitudes are same. That's why internal energy is a state function, because it does not depend upon the path followed, it depends upon the initial and final states only. Okay. So, it proves that internal energy is a state function. Okay. Any doubt? So, keep in mind Q and W are path functions, but Q plus W is a state function. Yes, anyone? So, let us define zeroth law of thermodynamics. That is not given in our book, but anyhow, it is very simple law. So, why do we left it? So, zeroth law of thermodynamics states that if A and B are in thermal equilibrium with each other, A and B okay, I explain it once again. See, if we go from from state A to state B by following this path, see, pressure is increasing, and volume decreases. Volume decreases. Okay, volume decreases, that means it is compression work. In path 1, compression work. Okay. At the same time, it goes from, that means volume decreases, work is done on the system. So work is done on the system, that means that heat is, what about heat? Can you? Yes, as internal energy increases, work is done on the system. So work, there is a compression work. Okay. Now when, let us talk about work only, and when we go from B to A, path 2, that means volume increases, so that is expansion work. That is expansion work. That means paths are different. In path 1 there is compression work, in path 2 there is expansion work, and heat is compensatory, because if work is done in the on the system in first case, then heat is released. In second case there is expansion work, so work is done by the system, so heat is absorbed. So say heat and work are different, but their sum is equal, because when we go from A to B and then back to A, see, internal energy remains same. Though work and heats are different, but total internal energy has no change. Got it? Okay, now zeroth law of thermodynamics. Now, what do you mean by zeroth law of thermodynamics? Actually, when A and B are separately in equilibrium with C, A and B, they are in thermal equilibrium with C. Okay, there are three systems. Okay, A, B and C. So two systems A and B are separately in thermal equilibrium with the third system C. Then they are also in equilibrium with each other. Very simple, right? Because if A is in thermal equilibrium with C, B is also in thermal equilibrium with C. So what it means? That A and B are in thermal equilibrium with each other. And what do you mean by thermal equilibrium? What do you mean by thermal equilibrium? Anyone? Okay, first I write the definition, okay, and you will write what is thermal equilibrium. So statement is, if two systems, let us say A and B, are separately in thermal equilibrium with a third system C, okay, then they are also in thermal equilibrium with each other. That is the definition. Okay. Yes, very good. Means they are in thermal equilibrium if two systems are in thermal equilibrium if there is no net heat flow. There is no net flow of heat between them when they are brought in contact. If two systems are in contact with each other and there is no net flow of heat, so that means they are in thermal equilibrium with each other. Means temperature should be same, because if one is at low temperature, other is at high temperature, then there should be a flow of heat. Okay, but if there is no net heat flow, that means both are at the same temperature. Very good, great. Ralam, Chitra, Abhay, Siddharth, great. Okay then, bye bye for now. It is 7:10. Or do you want to do one question? Let us do one question only, okay? One question. Let us consider a system absorbs 300 joule of heat and does work of 100 joule, okay, on its surrounding. Okay, so very simple question of seconds. Calculate the change in internal energy. Yes, fast. Very simple question. What is the answer? Question is, a system absorbs 300 joule of heat and does work of 100 joule on its surrounding. So calculate the, it is 400. Wrong answer. Say, according to first law of thermodynamics, delta U is equal to Q plus W, right? So as heat is absorbed, by the system, so heat absorbed means plus 300 joule, work, very good Abhay, Mansi, Ralam beta, say work is done on the surrounding, means work done by the system. So work done by the system is negative. Work done by the system is negative. So according to first law of thermodynamics, delta U, that is equal to Q plus W, that is equal to 300 minus 100. So it is equal to 200 joule beta. Okay, Ralam, Q plus A U, what is that? This is the formula we have derived just now. The delta U equal to Q plus W, and Q is positive when heat is absorbed, Q is negative when heat is released by the system. W is positive when work is done on the system. W is negative when work is done by the system. Right? So that's all for the day.